So in this role, Courtney Bowman also works with the privacy advocacy world at large to ensure that concerns related to new and emerging technologies and data sources are addressed in the ongoing design and implementation of Palantir software platforms. Bowman is co-author of the Architecture of Privacy, which I have made a preview of, which is really exciting to read, and I'll encourage everyone here who's interested in AI ethics to also read it as well, which provides a multidisciplinary framework for designing and building privacy protective information systems. So prior to Palantir, Bowman earned degrees in physics and philosophy at Stanford University and worked as a quantitative and economic analysis at Google. So very happy to have Courtney here today, and the floor is yours.
Cindy, thanks so much for inviting me, and it's very exciting to be able to address this group. This is going to be a bit of a whirlwind presentation. For those of you who are not expecting a philosophy lecture, you may be a little bit disappointed or pleasantly surprised. But what I hope to provide in the course of the next hour or so is an interesting critique, and hopefully a valuable critique that outlines some of the fundamental challenges that arise in artificial intelligence historically and still impact the state of AI, inclusive with the sort of modern focus on, or the current focus on machine learning. So I usually give a version of this talk with a live audience, and there's a component of this that I may kind of gloss over very quickly, but I try to make it a little bit interactive with a group to get people engaged. I will encourage you, if you have any burning questions in the course of the talk, to raise your hand and stop me, and we can try and address them. Otherwise, we can try and hold them to the end of the talk, because there is a fair amount of content that I want to run through. But I'm going to start off by, well, Cindy's already given an introduction, but I should mention that most of the content in this presentation I'm presenting in my personal capacity, although a lot of the approaches and considerations that are built into this view of AI and recognition of its limitations are things that are deeply ingrained culturally in the way that I work professionally in my role at Palantir Technologies. But again, this is primarily me pontificating from a personal perspective based on my own views of AI and what I think are some of the challenges and limits and also opportunities. So I want to give a few upfront definitions, just so we're all on kind of the same page in terms of what I'm referring to as I talk about some of these concepts throughout the coming slides and points of discussion. When I refer to weak or cautious AI, I'm referring primarily to the idea that computers give us powerful tools that tend to be domain specific, or for special purposes, and oftentimes the relevance is decided beforehand. And by and large, I think this is what we tend to think about when we talk about artificial intelligence today in most applied contexts, and in fact, in most research and development contexts. Contrast weak or cautious AI with strong, full, or general or artificial general intelligence. And I use those terms interchangeably. I recognize that some commentators have draw some distinctions among those, but I will use them interchangeably. And this I refer to as the notion that computers appropriately programmed really constitute a version of minds themselves and are able to carry out general knowledge applications. And in this context, they're able to form representations, their own generative representations to solve significant problems spanning many different domains that we tend to associate with human cognition. And then I'm relying on a very general notion of machine learning, the idea of using statistical techniques to give computers the ability to progressively improve on a specific decision-making set of tasks. I'm being agnostic as to the specific class of machine learning, recognizing that there are different methods for approaching that type of data analytics and artificial intelligence application. And then finally, I'm going to be referring a bit to a notion that's drawn from philosophical literature. And broadly speaking, this idea of intentionality is the property of the mind or brains by which it's able to represent other things. So this includes extra linguistic goals and aims that orient speech. And oftentimes when we talk about intentionality, we're talking about intentional states that reflect situations in the world and how systems or programs interact with those situations in the world. And so this is the interactive part, or a early interactive part. It's a little game that I like to play. It's called Can You Guess the Year? And we'll see if this works. We'll go through a few iterations, but I'm throwing up a few quotations on the board. And I want people to shout out the year at which they think this statement was made. And these statements all come from pretty prominent members of the AI community. So I'll also encourage you to maybe either speak out vocally, or if you want to throw them into the chat window, I have that open. But can anyone guess the year that this statement was made? I see one guess from Rob Casey of 1955, 1970, another guess, 85. Any other guesses? 1980, 1950. Okay, this is a pretty good guesses. This statement was actually, let me see if I can advance my slides. The statement was actually made by Simon and Newell in a publication in 1958. So let's try another one. Machines will be capable within 20 years of doing any work a man can do. Anyone want to guess when this statement was made? '70, 1920s, 1898. Okay, it's a bold guess. 1900. All right, so people are kind of picking up on the concept here and throwing out some pretty early guesses. Looks like somebody got it spot on. This is another published statement by Simon in 1965. Great guess, Alan. Okay, another one. Within a generation, few compartments of intellect will remain outside the machine's realm. The problem of creating artificial intelligence will be substantially solved. Quick guesses here. '1981, 1970, 72, 50 again. 1967. Okay, and then one final one. In 3 to 8 years, we will have a machine with the general intelligence of an average human being. I won't wait for your guesses because I think you're all picking up on the theme here, but this is another statement that was made by Marvin Minsky in 1970. And so what I'm kind of drawing out is that in the early stages, or the early decades of artificial intelligence, there is this sort of wild exuberance and feeling that the state of the technology had advanced to a point where we were very close, on the order of years, a handful of years, in some cases decades, to be able to basically solve the problem of artificial intelligence in the generalized sense, to be able to create artificial general intelligence that's capable of carrying out basically all human tasks. And the question is, we're clearly not there, right? Here we are in 2021, and we're in fact quite far from AGI. And the question is, what went wrong? Where did we fall down? Where did we get our early estimations so far off from the reality and the capabilities of what the technology allows? And I think one answer to this question comes in the form of what's been referred to in the literature as the first step fallacy. And it's the idea that the first steps in research are indicative of progress, and the presumption that progress is enough to carry to the next step level. But this, in fact, is a bit of fallacious thinking. There's a few different formulations of this first step fallacy, but I think one of the metaphors that I like the most comes from a systems researcher called Stuart Dreyfus, who says it's like claiming that the first monkey that climbed a tree was making progress towards flight to the moon. And I think that statement actually is very illuminating in terms of understanding what's happening with AI, in being able to solve a certain class initially of deductive logic or deductive reasoning challenges, and then assuming that somehow will provide insight into the more expansive set of cognitive tasks that constitute the full range of human thinking. There's clearly a chasm between climbing a tree and leaving orbit. And that chasm is very indicative of the challenges that we've encountered in a lot of different spaces of artificial intelligence. So I want to now just kind of give a quick a history, or at least a view of my history of the development of AI. And most of these considerations, I think, will be familiar, or these touch points in the history will be familiar to most of you. But I'll move fairly quickly. I think of AI, even though they're arguably even earlier roots, but the modern era of AI and its early history starts with the Dartmouth Conference. And the founding conjecture of that conference was the idea that every aspect of learning or any other feature of intelligence can be in principle so precisely described that a machine can be made to simulate it. And it's worth taking into consideration why the Dartmouth conference happened at the time that it happened and what was motivating it. At the time, there was very significant progress in neurophysiology. We were getting closer, we believe, to understanding how the brain works. And that led to a number of researchers assuming or presuming that there was significant progress towards the idea of being able to simulate the function of human cognition. And so that led to the Dartmouth Conference, which was a kickoff for what I refer to as the tool building period of AI, or as his term coined by Bruce Buchanan. And this is basically constituted in the idea that cognitive simulation work in language translation, problem solving, and pattern recognition made early progress. A number of programs proved to be quite effective at doing things like basic theorem proofs. And then the tool building period flows into what I refer to as the semantic information processing period. And this is a period where good old-fashioned AI, or GoFi, as symbolic systems was the significant area of focus, as well as a real focus on heuristics, trying to synthesize rules of thumbs that humans use to solve problems, and track those into computer programs to carry out specific tasks in the space of things like building chess-playing machines and other game-playing machines. And then things start to go south. And that movement south is really poignantly captured in the Lightail report, which I strongly encourage folks to read. It's a 1973 report by the British government that looks at some of the failings of the very heavy investments in UK academic institutions and how they failed to produce any of the significant outcomes that researchers claim that they were making. The Lightail report plus similar recognitions on the other side of the Atlantic, with DARPA starting to cut back its own research and development funding, really spells the beginning of the first AI winter. So the first AI winter I denote as taking place from about 1974 to 1980, and it's worth defining what an AI winter is. The American Association of AI in 1984 actually coined the term as a chain reaction that begins with pessimism in the AI community, followed by pessimism in the press, followed by severe cutback in funding, followed by the end of serious research. And that definition is actually quite poignant because we see at least one other cycle of AI boom and bust. The next boom cycle happens in the early 80s. With primarily focused on what were called expert systems. And then we also see a turn towards early versions of connectionist AIs, the early forms of neural networks that have also been sort of recast in the modern era. And then most significantly, we saw governments taking a leading role in driving research and development. So particularly Japan announced an international trade in industry association event, what they call the 5th generation of computing program, which of course was then matched by a DARPA project called the Strategic Computing Initiative, which both spelled a very heavy investment and almost a race towards artificial intelligence developments. You might think about, are there other analogous races that are taking place today? Just we'll plant that seed in your heads. But unfortunately, this second AI boom also led to a collapse. So around 1987, 1988, the Lisp machine market, which was a computing market that was focused on very specific tools for broad AI or broad computing, but also for AI, collapsed in light of the PC coming to the fore as a generalized tool for computing. DARPA canceled its strategic computing initiative. Japan scuttled very quietly its fifth generation computing project, and then the notion of expert systems really started to bottom out. And so that winter, AI winter, lasts until about 1993, and then in the early 90s and into the early 2000s, we see a gradual thawing. But having gone through two boom and bust cycles, there's a real reluctance to talk about artificial intelligence as such. And in fact, in the early 2000s, you see very little mention of the phrase, in part because people were burned, and there was a sort of taint or stigma that attached to artificial intelligence. So you see advanced analytics and AI in any other name. So things like informatics, general analytics, knowledge-based systems. Basically anything people were attempting to call anything or advanced analytic systems, anything other than artificial intelligence. In contrast that today, where basically any type of advanced data analytics is labeled a form of artificial intelligence. But at the time, that concern about the stigma of failed programs from prior boom and bust cycles really did create a mark on attempts to build AI. And so that the thawing produces a gradual quiet spring, which I think really started to bloom in the mid-aughts. And it brings us into what I would refer to as the modern era of AI, where a confluence of factors, including the rise of computing power, lower cost of fueling development of machine-intensive techniques, also general availability of a lot of data, revival of neural networks as a tool for machine learning, and building more advanced statistical modeling, sort of reinvigorates this interactionist model and connectionist model that has taken fruition as various forms of neural network machine learning. But I would argue, and I think that the trajectory of the remainder of this talk may suggest there's a risk that we may be moving into a third AI winter. And you start to see signs of this in various places. A growing chorus of concerns, particularly in the fairness, accountability, AI realm and explainability AI realm. There's lots of struggles to get to some kind of common agreed upon assessment of how to deal with these challenging normative questions. So the general call for AI ethics and the growing amount of regulatory pressure to rein in AI practices is creating potential drag on the development of technology. But I think it's also calling attention to a deeper set of issues that I'll get to in a bit. We see things like major institutional investments like Watson fizzling out, essentially, showing none of the significant gains that were demonstrated in early programmatic attempts. So Watson, as a Jeopardy playing tool, really failed to translate into a marketable set of applications in industry. And then from a lot of practitioners, researchers, and commentators, you see growing chorus of skepticism. And I'm going to try and in the remainder of this talk explain why I think this skepticism reflects a set of concerns that are deeply ingrained in artificial intelligence, and in a way that I think suggests that AI doesn't just have an ethics problem. It has a more fundamental metaphysical and epistemological and deeper philosophical set of problems. But to sort of give you a modern example of where we see recurrence of historical patterns, just look at automated vehicles. And I like to go through the kind of series of statements that we see emerge from Tesla and Elon Musk. And it's really this very consistent pattern of sort of hyped claims about AI capability or automated vehicle capability. So starting in at least 2016, but probably earlier, claims from Musk that every future Tesla vehicle will be capable of driving itself, and promising that this is going to take place in 2017, a full coast-to-coast trip that will demonstrate this capability by 2017. And then we get to 2017, and Tesla announces that it's expecting to demo run a full level 5 autonomous vehicle capability in 3 months, maybe 6 months at the most. That doesn't happen. We arrive in 2018, another series of statements from Musk. It's another 3 to 6 months. Skip ahead to August 18th. Definitely going to do a coast-to-coast demo towards the end of the year. Doesn't happen. April 2019. Musk estimates that by the middle of 2020, Tesla's autonomous system will have improved to the point where drivers will not have to pay attention to the road. And makes even bolder claims that in a year, there will be 1 million robo-taxis on the road. And it goes on and on. In April 2020, the expectation that the robo-taxi fleet is about to be released, but the only problem is regulatory approval. And then further statements that autopilot system will be released in a month or so. Doesn't describe the capabilities, gives a suggestion that autopilot is level 5 autonomous capability, when in fact it's far from that. So it's this consistent cycle of hyping capability that I think reflects the same pattern that I pointed to earlier, this first step fallacy, the belief that early efforts and early gains in capabilities like automated vehicles will translate necessarily into fully autonomous capabilities and full level 5 driving. But it doesn't happen. Arguably, if you look at commentary by, I think, some pretty credible individuals in this space, we're very far from getting to full level 5 autonomous vehicles. Let me just pause here because I want to see if there's any burning questions in the audience. Anyone want to raise a question?
Rob has raised his hand, yeah.
This is a great introduction so far. Really got the wheels turning. I'm curious about, what do you think was the critical pivot point for this latest hype cycle for AI? What kind of technology or research emerged that really got everybody running to the AI races?
I think it's probably a mix of things. It certainly is the cloud computing as a resource that's broadly available and cheaply available has opened up new avenues for anyone with a little bit of cash to be able to do some significant AI development. There is some accessibility of data, although if you look at a lot of the proposals for additional research and development efforts, they're focused and concerned about a lack of generalized data assets. But arguably, I think there is a fair amount of data that's available, certainly in the private sector, certainly in certain aspects of government, and in some places in academia. But there are also some pretty powerful data sets that are available to the public to be able to do independent research. I think one of the other significant drivers here, and this is what I was alluding to earlier, is I think there's a growing call towards an international arms race in artificial intelligence. And it's a reflection on the current near-peer kind of adversarial context within defense and geopolitics, where you have these poles of power, namely the US, Russia, and China, and maybe to some lesser degree the European Union, but all trying to compete and make claims, or increasingly bold claims, about the ability to capture this AI space. I think those factors combined together really driving a lot of the efforts here. On top of that, I think there's a significant influx, is an ongoing influx of money that's pouring into this space. So all of those things kind of create the groundwork to be able to do a lot of new AI research and development. Whether or not it materializes into something that actually is applicable and useful is another question. Any other quick questions before I keep moving? Okay, I don't see any other raised hands, but let me keep going. So This is the part of the talk where I start to wax a bit philosophical. And I'm going to make a case against an unbridled AI optimism. And I should say up front, my position here is not one of absolute skepticism. I'm not trying to say that there's no prospects of AI and that AI should be shut down entirely. If anything, the positive turn on my narrative here is that if we actually want to capture the gains of artificial intelligence in its modern instantiation and continue to have reasonable budgets to be able to carry out research and development and pursue new initiatives, it's going to require some moderation of expectations and some more realistic views about what the technology can and can't do. And my view is that that realistic view needs to be grounded in principles that are currently kind of lost in this space of hype. So I want to try to articulate why these sort of philosophical considerations actually matter. Starting with a bit of a background on thought experiments that are kind of instrumental in how we think about AI. So most people are familiar with the Turing Test. The quick recap here is the Turing Test is a reflection on a game that was played in parlor rooms in the 50s and earlier, called the imitation game. And the principle of the imitation game is you have two people behind a veil, and you have a third person that's asking them questions. And the whole idea is to try and, if you're answering questions, elude the questions to convince your opponent, the person who's asking the questions, that you're something that you're not. So you can play the game where you're asking about the gender of the person who's being asked questions, and the idea is to convince the other person that you're not the gender that you are, to basically trying to convince them of a lie. And the idea with the Turing test is essentially, can you replace a machine with one of the contestants in this game? And you can carry out whatever machinations you need to. Instead of having people declare their answers in voice, you can have it through a printed screen. So you don't know if it's somebody at a terminal or a machine. But the idea is that if you can create a program that can play this game well enough to beat contestant C often enough, then they pass the Turing tests. And in many respects, this is kind of a low bar for human cognition. It reflects a pretty well-defined game space. But this is often what we think about when we think about whether AI capabilities are capable of matching human cognition, at least in some narrow sense. But a philosopher at Berkeley in the 80s posed a counter thought experiment called the Chinese room. And the idea with the Chinese room is that let's take an individual who has no formal training in the language of Chinese and put them in an enclosure and give them a very complete translation book that basically allows them to receive incoming Chinese text, which they view more or less as squiggles, look up some translation in the book that they have, and then spit out an output that takes that comprehensible translation and turns it into something from the output angle that looks like a Chinese response to an incoming Chinese question. And so the question to think about here is, given the way that I've described this experiment, can you actually say that the person inside the room who's carrying out these instructions, who's looking up the squiggles and matching them to other squiggles, can you say that this person understands the language of Chinese? And the standard intuition here is absolutely not. Under no circumstances would we say that looking up squiggles and matching squiggles to other squiggles is a comprehension of a language. And so the question then is, if we wouldn't say that the human in this box is understanding, is a cognitive agent in understanding the language of Chinese, why would we say that a machine doing the same function, this formal function of translation, is a cognitive agent? And that's supposed to lead us to the conclusion that it's essentially not. So we tend to kind of arrive at the idea that this is an understanding of Chinese. It's a formalism. And I should be clear that in Searle's thought experiment, he's not claiming that all machines are incapable of thought. In fact, he's agnostic to the prospect and leaves it as an open question. And he's also saying that he's not saying that no man-made machines can think. But what he is saying is that the type of information processing that's conceived in the Turing test and that's carried out by digital computers has fundamental limitations in the nature of how it processes data. And those limitations can be framed in view of this term that I defined earlier, this term of intentionality, where intentional states are defined in terms of their content, not their form. And the distinction here is that there is a material difference between the form of how we carry out processes and the content that relates to actual things in the world and situational experiences. And this is supposed to tease out an intuition that when we think about what it is that machines are doing in ML processing and other forms of artificial intelligence, that they're doing something. They're processing data. They're processing data in useful ways according to algorithmic determinations and representations. But what they're not doing is thinking. They're not actually carrying out the acts of understanding that give knowledge and cognitive actions real meaning in the world. And so those thought experiments are meant to tease out initial intuition, but I want to go a layer or two deeper and draw upon the philosophical thought of another Berkeley professor called Hubert Dreyfus, is a philosopher that I'm quite fond of. Who I think goes deeper into this idea of what it is that human information processing involves and why systems, computing systems and their method of processing information is fundamentally different in ways that are incompatible with the expectations of human thought. So Dreyfus comes out of a school of philosophy that I have a great regard for. It's called phenomenology. It's a sort of subjective theory of consciousness that looks at the way that intentional states relate to beings in the world, beings who have embodied status, are situationally dependent, but also sort of breaks down the subject-object distinction that's deeply entrenched in Western philosophy. And we don't need to know all the background because Dreyfus gives a pretty distinct set of properties that he associates with human consciousness that are also very hard to replicate in machine systems, but also in many ways are critical to the way that we process information in a lot of contexts. So the first point that first characteristic that he points to is this notion of fringe consciousness. The idea that there are millions of things that we're aware of, but we're not really thinking about directly. We're not immediately processing. And we don't always know what all of those fringe consciousness elements are. But one way to make this very intuitive is in the classic Gestalt pictographs, where if you look at one picture and stare at it long enough, the one on the left, you see a vase. If you stare at it a bit more, you see two faces looking at each other. And on the right, similarly, if you look at it in one way, you see a tree, and another way, you see a lion and a gorilla staring at each other. But it's the totality of that experience, the fringe elements of those images that really snap things into meaning. And it's not clear how you actually translate between those two representations. But when it happens immediately, and it's very clear what's happening. But this is actually something that's very hard to replicate in machine settings. In a similar sense, we do something with the way that we process information, which is that we oftentimes have very limited information in very complex settings where there's fundamental ambiguity in what we're trying to describe. And this ambiguity tolerance is something that you can think about in Wittgenstein's classic example of defining a game. There are many different types of games, and trying to come up with a universal definition of games is actually an impossible task. Because there isn't really a strict notion of what it is that constitutes a game. Instead, we have what Wittgenstein refers to as family resemblances. But this ability to deal in ambiguity and process information where there aren't clear definitions is one of the things that's fundamental to human cognition. It's very hard to capture in machine systems. You can take example in natural language processing of the sentence of the box was in the pen. This is a classic example from a Bar Hillel paper in the 1960s that I highly recommend. This is actually an incredibly simple sentence that's extraordinarily difficult to make sense of if you're not a human being and you don't have human context. Because it can mean any number of things, but what it actually refers to, if you put it in the context of an additional set of sentences, is little John was looking for his toy box. Finally, he found it. The box is in the pen. The pen is a playpen. John was very happy. And you can see why the ambiguity that's embedded in things like language and also vision and a number of other commonplaces of AI creates some really fundamental challenges to making sense of what is otherwise very simple sentences. And the final characteristic I'll talk about is the essential inessential discrimination ability. And this ability to distinguish between what's essential and inessential is a fundamental human form of information processing. And it's something that's very hard to do. And a number of attempts in AI have tried to articulate this concept and build out expanded bases of knowledge. But the reality is, what you often find is that in order to make sense out of a discrete set of details, you have to go one layer out, and then you go another layer out, and you realize that you still are lacking maybe a fundamental idea of the physics of the environment in which you're operating. And all of these things become very difficult to embed in the system. And it isn't clear how far you need to go out, whether you need to encompass an entire universe of information, or if you can have a more discrete world to focus on. And this is clearly a challenge for AGI, but I would argue it's also a challenge in a lot of spaces of application of weak artificial intelligence. But in fact, the AI's problems go well beyond what we often talk about when we talk about AI being fraught in an ethical sense. And what I'm trying to draw out is that there's some very basic categorical challenges in the way that AI is constituted. And I think that follows from 4 assumptions that support the historical optimism around AI. The first is that, and this goes back to the point that I was drawing out in the early days of AI with the Dartmouth conference. There was a presumption that the brain processes information in discrete operations. And that somehow, if we have a good model of those discrete operations, and we know that we have transistors that operate similarly as binary switches, if we just stitch a lot of transistors together, we can come up with a physical model of the brain. That's on the biological level. On the psychological level, there's a view within the AI community that the mind can be viewed as a device operating on bits of information according to formal rules. And then we skip to the epistemological level, the idea that all knowledge can be formalized. That is, whatever can be understood can be expressed in terms of logical expressions. And then finally, there's the ontological assumption that since information is fed into digital computers in the form of bits, that a computer model of the mind must in principle be analyzable as a set of situation-free determinate elements, that you can take those bits of information, pour them into a machine, and end up with an ontological model of the universe that's fully kind of self-sufficient. But the reality is all of these assumptions are fundamentally flawed. So the first assumption, the biological assumption, has been shown through empirical research that actual neurons are much more complicated to model. They're not exactly binary switches. They have impulses that are tuned to certain levels, and it's more of a gradient than an actual binary firing. And then that's at the very basic level. The way that neurons interact with each other is a much more complicated situation. And even though we built AI models that presumably have the same number of neurons as, say, the central nervous system or the brain of a nematode, we still can't actually carry out all the functions of a nematode. And that's because those systems are actually much more complex biologically than we presume them to be. Then there's the psychological assumption. They're actually complex attitudes and tendencies, and the unconscious background that's essential to processing information in the human context is something that we don't fully appreciate. But we can see inklings of why it's problematic in the mention that I made before of tolerating ambiguities. and navigating those soft edges that really do create the fringes of our consciousness and awareness. And I'll pause after I finish this slide because I see that there may be some questions that are jumping up, but I want to quickly run through the epistemological and the ontological assumptions as well. So it's a reality that a significant amount of human knowledge is not actually symbolic. It's situational. There's no number of symbolic representations that we can put together to describe how we think about being in love, or the feelings that we emote when we read great poetry or read great pieces of literature. Those aren't symbolic propositions, but they're fundamental to how we characterize our being, and they're fundamental to how we operate and interact with the world. And then lastly, the ontological assumption is actually grounded in a philosophical tradition that it confuses the world for the universe. So it fails to distinguish between human situations and the state of a physical system. Another way of thinking about this is the universe is a set of representations that maybe we think about in the sense of physical principles. So physics gives us a theory of how the universe operates, but that actually doesn't tell us much about how to live our lives, what good choices we should make. And that lived experience of the world versus the reductive version of the universe is actually a massive ontological chasm that oftentimes is overlooked, not just in AI research, but in the history of Western philosophy. So let me really quickly pause. Any burning questions right now before I keep moving? Rob again. Go ahead, Rob.
I was wondering if you could speak to the role in the 5 human senses that plays into situational knowledge, human response, and basically just kind of the overall processing of knowledge and decision making that goes on in humans versus machines that are largely locked out of such sensory input.
Great point, and you're anticipating the content of the next slide. And so let me just get to that naturally. The final considerations that I want to walk through is that data is not information, and this is precisely for the reasons that Rob is starting to allude to. When we interact with the world, we interact with the world through all of our senses, through embodied experiences. But when we program machine learning systems and artificial intelligence, we're taking sensory outputs that are already reductive in some form. We're translating them into some structured format or semi-structured format or symbolic format, which is another form of reduction. And we're calling that data. But that data is not the world itself. And there's something lost, and there's some fidelity that's lost in that series of translations. And then there's more fidelity that's lost as that information gets processed through some set of algorithmic processes. We have to acknowledge that the way that we process information as beings that are interacting with the world constantly through our bodies, through our 5 senses, is fundamentally different from what a computer is doing when it takes sensory output that's translated into binary bits, that's then translated into rows and columns, that's then run through an algorithm to produce some statistical set of considerations or parameters or outputs. Those are fundamentally distinct things. And they speak to this broader concept of our life is a situated life. In philosophy, there's a term Lebensform. It refers to this generalized experience of being in the world that constitutes the human experience. That's fundamental to how we process information. And we haven't yet built machines that are capable of emulating that because our machines are built on a very different kind of physical model. So physical embodiment is critical. There's just a place for background practices, the common sense that defines our experience. That's really hard to encapsulate in a discrete body of knowledge that we can program into computers and AI. There's just a fundamental distinction between knowing how and knowing that. It's the distinction between competence and performance. So you can take someone who's never ridden a bike and you can lay out all of the physics and the theory of what it means to ride a bike and put them on a bike and say, hey, you have everything that you need to know. And I guarantee you that on their first try, they're going to fall. And it's not for lack of knowledge. It's for lack of knowing how to do the task. And another way of framing this is when planets are orbiting, they're orbiting the sun. They're not continuously calculating partial differential equations to stay in orbit. They're just doing it because that's how the universe works. So there's a distinction between knowing how information is processed or knowing a theory about how the world works and actually applying it and doing it in practice. We also run into this self-referential and recursive set of problems that I think is most emblematic, for example, in natural language processing, that the meaning of words depend on the meaning of the context, which also depends on the meaning of the words, and so on and so forth. And you run into these recursive challenges that are hard to program your way out of. And finally, I'll point out the framing problem that AI and ML tends to perform well in well-constructed representations in game situations where there's a clear outline of the field of play, there's a clear set of rules, and the method representation or reasoning over the set of rules is well-defined. But that's a difference between deductive and inductive reasoning. And even in machine learning, the inductive capabilities that we build out prove to run up against a number of challenges, which we can talk about if we have sufficient time. But this is often referred to as Moravec's paradox, and it's the paradox that machine learning and AI has at this point gone pretty far distance in being able to emulate very high reasoning, high functioning, well-defined tasks like playing chess. But when it comes to teaching a robot to walk, basic tasks that a 3-year-old can do, the programs tend to fail miserably. And it's because these less well-defined problem sets in environments are actually much more complicated because the rules are not well-defined and there's so much ambiguity and situational context that's deeply embedded. So very quickly, having kind of made the philosophical case, I want to make a few points from an empirical perspective. And the primary points here are that those of us who've worked in data science and built models and tried to apply those models in any given context in the world have seen some of the brittleness of the application, that models break down over time because the world is changing, the data that's input is changing, the method for processing is changing. They don't easily translate from one context to the other. And even advanced machine learning models don't actually learn to adapt in the way of reforming the representations that are necessary to retrain towards new contexts in the world. So this is a fundamental problem that really hasn't been addressed sufficiently in the space of machine learning and more generally artificial intelligence. But computers show us time and again that they can analyze patterns of data, but they can't make sense of things in the world. They can't kind of cross that semantic gap, the chasm that we have represented as this intentionality concept. And the reason they can't do that, and this goes back to the Chinese room experiment, thought experiment, is because computers fundamentally don't understand. They're systems for carrying out algorithmic tasks, but at the end of the day, they don't understand what those tasks mean in the context of the world in which the tasks and characteristics play out. And very quickly, example that we're all probably quite familiar with from the space of adversarial AI research. You can build, for example, a program that is very good at computer vision and image detection, highly well trained for identifying, for example, a school bus or a temple. We know that you can layer on some distortion that's then utterly unrecognizable to the human eye. But the output of the model would tell us that both of those slightly rectified images or slightly modified images are both ostriches. But when we as human beings look at these things, we can see that that's clearly not the case, at least not in any sense that would be meaningful to us, because the understanding that's embedded in the images as we process them is fundamentally distinct from the binary units of information that are processed by the computer vision algorithms that have been attacked by this adversarial attack. So I'm getting to the end, I promise, or getting close to the end. I wanted, a lot of the arguments that I've made throughout the last, I don't know, 50 minutes have been, you could argue, more directed at strong AI, at AGI. But I actually think that most of these critiques are endemic within weak AI applications and do apply to how we think about weak AI. And the challenge remains that there's a whole world of intentional cognitive states that can't easily be outsourced to machines. And so even when we take weak AI as a method of building machine learning models or artificial intelligence to carry out specific tasks, those tasks may still be embedded in the world, rely on some very basic but challenging to program assumptions that go beyond the scope of what we can easily program into our AI systems. And so recognizing that as a limitation and a risk is critical to being able to situate the technology in a way that makes sense and makes it guided, as opposed to presuming that it's capable of performing magic. And I would argue that that's essential to being able to do AI in the weak or narrow sense in a responsible fashion. So how should we think about how computers should be used for algorithmic decision making and what decisions are appropriate to hand off to a computer? These are the fundamental questions that should be drawn out of what I've been presenting. And the guiding principle that I would put forward and hope that sticks, if there's one thing that sticks in this presentation, it's the idea that computers don't understand. I would really challenge you all to try to internalize that message and think through what the implications are of that fundamental intuition. And I think another way of framing this kind of allegorically is we really have to move away from the idea of AI as a magic beanstalk, as something that's going to bring us to the moon. And instead think of AI as much more of a tool, something like a ladder. And in fact, it's not even that idealized version of a ladder. It's a ladder in situ, meaning that it's constantly embedded in an environment where the environment can produce degradation, where it's attached to a bunch of different glue code that could break down, where data vulnerabilities can undermine its function. All of these things point towards the idea that AI is really a tool, not a panacea. And we know this, we know that the world is complicated and it's ever changing. We also, I think, generally would recognize, most of us, that we're a very long way from AGI or strong AI. But my argument that I tried to point out is that even weak AI and ML remains deeply fraught, and there's some real challenges with brittleness, with lack of critical understanding and normative and understanding and ability to deal with normative attachments that shape the way information should be processed in real life situations. And so algorithms and ML and AI are best thought of as tools and not as a panacea. And really that should reorient the way we approach ML and thinking about the centrality of humans, because humans really are alone positioned to be able to figure out the appropriate legal and normative and ethical trade-offs for dealing with these complex situations, because humans understand in ways that computers, at least in current form of computers and computing systems, just can't do. So the final thought before I'll stop is another set of quotes from, again, Hubert Dreyfus, who's kind of the hero of this story. It's the sort of warning that we may find that we're not about to achieve a sort of Terminator view of the world where machines gain sentience and decide to kill off humanity. But more likely what we're at risk of doing, instead of building super intelligent computers, is making sub-intelligent human beings who expect the wrong things of artificial intelligence and derivative technologies like machine learning. And because of that, degrade our intuitions, degrade our ability to check these technologies, make false assumptions, and ultimately undermine our own cognitive capabilities to do the things that we do best. So with that, I will stop and thank you all for listening to me for the last hour.
Thank you, Courtney. I think we have 2 questions so far. Maybe Rob, you can shout out your question, and thank you for such a wonderful talk, Courtney. I really enjoyed it a lot.
Yeah, my pleasure.
Did you want me to ask my question?
Oh, sorry. I see it.
Oh, okay.
Go ahead. Yeah. Go ahead, Rob.
Yeah. So it makes me think that that Dreyfus quote was really prescient to what we're dealing with today. And I just wonder if, the nature of AI, if, like you say, we're probably pursuing it sometimes in the wrong direction by trying to make them more human-like instead of making them a useful tool. And I just wonder if one of the fundamental differences is the nature of understanding, where computers don't understand, is maybe because there's a critical link to the notion of self-preservation. And, because we're pattern matching and predictive individuals, we're always trying to, improve our life situation or improve our safety through trying to figure things out in the world. There's an inherent motivation to understand things. And machines don't have that inherent motivation.
Yeah, I think it's an interesting point to explore. There certainly is something that's in our nature to want to understand the world around us. But I think that the statement that I just made, I think it starts to give you a reflection on why that is the case. And it is because we're alive and breathing and interacting with this world. So it's not just a desire, but it's something that we actually have to do on some level to be able to adapt to the changing circumstances that we're in. And it isn't clear to me, and again, I'm not making the claim that machines or some form of artificial intelligence could never do this thing called understanding or have intentional states. But I think what happens when you go through this laundering cycle of trying to emulate processes in the brain and assuming that brain equals mind, mind equals a view of an ontological view of the universe and understanding, and somehow you can jump between those kind of very modest and scaled down and reductive models into something that's fully fleshed out, is going to get you to the human understanding concept. There's too many things broken in that chain to get us to the point that you need to be able to do real cognitive patterns in the model of humans. Now, it may be the case that we build another class of machines that represents a new type of intelligence that we haven't thought of. But I would argue that we're very far from doing intelligence in the form that we think of intelligence, in part because I don't think we fully understand what intelligence means. What I articulated is mostly some of the challenges in defining intelligence and making sense of it in all the critical contexts in which it matters. But taking that ambiguity and set of misunderstandings or faulty understandings or limited understandings and translating that into a full representation of or a full model of how to create artificial intelligence, we're very far from doing. And my intuition here is that if we were ever to get to some version of real artificial intelligence in the form of AGI, it's not going to take the form of computing systems, or at least none of the computing systems that we have right now. It's probably going to require something more organic, some type of wetware that is very far in the future, very far from where we are today. I don't know if I actually answered your question, but maybe that points in some direction towards a response.
That's great, very good observations. Thank you.
I think Jensen has raised his hand, and I just want to quickly say it's 1:03 p.m. Courtney, I know that you're supposed to leave at 1 p.m. and I think people are slowly leaving. But if there's no time constraint on your part, and if this room is not going to shut down, we can continue this conversation. But Jensen, please take it away, and Courtney, just shout out when you have time limits.
Yeah, sure. Thank you so much, Courtney, for the amazing talk. I just have a quick question regarding to this community is Earth system science. Actually the machine is doing a lot of amazing things that no human being can actually do. So we are actually increasing the intelligence level of the machine, not the human beings. We're not mimicking human intelligence, but the increase the model capability, like prediction accuracy, something like that. So what do you think that the weak AI, strong AI, so that kind of understanding capability can impact that kind of the existing Earth system capability? What do you thought about that?
Yeah, and it's a great point. So Cindy and I met through an Earth Systems conference panel in which we both presented. And I gave a very different talk that was focused on more making an argument that there's a set of ethical considerations that factor into the use of AI and machine learning, and even in the ML context of Earth sciences. I don't dispute, in fact, I agree strongly that machine learning is a very powerful tool for processing large amounts of information. And for certain classes of information processing where you're carrying out a well-formed model, there's incredible value in doing that. And it's a value that can't be replicated by humans, or at least not within the timescales that are necessary. So I definitely recognize the value of carrying out certain types of modeling exercises. The point that I'm trying to draw out is that taking those modeling exercises and then translating them into spaces where they may not apply or shouldn't be readily applied is where things start to break down. And so I would urge some caution and understanding that even in the earth sciences, where you're building, let's say, climate prediction models, there are places where the kind of normative glue that attaches those models and their outputs to the world really does matter. And the notion of that mattering is not something that the models are going to tell you. They're not going to tell you that, let's say, urban coastal communities with low income and minimized ability to be able to handle significant weather threats are maybe being misrepresented in data, are going to create a sort of unlevel playing field where you have disproportionate or unequitable modeling outcomes that disproportionately advantage the wealthy and disadvantage those who don't have significant means. Those are the sort of the edges of where processing information comes up against the challenges of applying that information processing to seemingly benign contexts like the earth sciences. That's where you kind of need to be careful. But I do agree that there are certainly cases where ML and weak ML has enormous value, and it's proven value, and we should continue to capitalize on that value. We just need to be careful to not get too ahead of ourselves and imputing in that value some grander idea that there's a sentient thinking behind that. And then that leads us to understand what the limitations are, that there may be things like embedded bias, or there may be contextual misunderstandings that makes it hard to translate that information processing from one context to the next. That's the way that we keep these insights well-grounded and producing continuously good results. And maybe I can, I'm gonna have to take off, but maybe I can do one last question.
Yeah, I think there's one last question by Rob, a different Rob. And I think he has a question about diversity and organizations. So maybe Rob, you can either read it out or Courtney can do it.
Oh yeah, hey, thanks for the great presentation, Courtney. Just wondering how at big companies like Palantir or other organizations you've worked with, you see kind of more diverse voices, or experiences where you haven't seen more diverse voices being brought to the table to work on some of these technologies. Just hoping you might be able to touch on that.
Yeah, so I should clarify, most of the work that we do at Palantir is more on the data platform and operating system side. So primarily what we provide are systems that are meant to enable responsible AI implementations. Largely speaking, we're not building AI, we're not building machine learning models for our customers, but we're giving them the tools to be able to manage their data and use that data to do advanced data science, inclusive of machine learning. But part of that process of building the means of carrying out ML exercises is being really thoughtful about the risks of how competent, responsible, efficacious AI needs to be done. So we tend to focus on making sure that there's a lot of thoughtful, diverse voices at the table. It's one of the reasons why my team is so involved in this work. We come from a lot of different perspectives, both in terms of biographical background, but also disciplines. We're composed of people with mixed backgrounds like mine in physics and philosophy, but also lawyers, social scientists, ethicists, computer scientists, and a handful of other domains. And the intent is really to bring a lot of these different perspectives to bear, because when you try to build systems that are only meant for, or only designed from the perspective of kind of a narrow view of an engineering challenge, and that engineering challenge actually has significant attachments to the world that implicate all sorts of ethical, normative, legal, social, as well as technical challenges, you're going to fall badly short. And so you really do need to deeply interrogate the design principles that come into play, how you develop these technologies, even if it's at the base layer of providing tools to enable machine learning, short of actually building machine learning techniques and models.
Great.
So with that, let me thank you all for being such a wonderful audience, and for all of the excellent questions. I hope this was instructive. And Cindy, thank you so much for inviting me.
Yes, thank you so much. And I'll be in touch very soon. Thank you everyone for participating in this meeting, and you'll soon see the recording online. Thank you.
Take care, everyone.
Bye.